Κύριε Αλιβιζάτο, κύριε Βόκαλη, αγαπητοί συναπόφοιτοι του AIT, φίλες και φίλοι από τα alumni club των πανεπιστημίων Berkeley, Bentley, Columbia, κυρίες και κύριοι, σας καλωσορίζω στην απόψινή μας εκδήλωση. Είμαι ο Γιάννης Τσιριλάκης, Senior Wireless Product Manager της Huawei και έχω τη χαρά να εκπροσωπώ απόψε το Σύλλογο Αποφύτων του AIT. Είναι μεγάλη μας τιμή σήμερα να φιλοξενούμε στην ετήσια εκδήλωση του συλλόγου μας τον Διευθυντή του φημισμένου Lawrence Berkeley National Laboratory και καθηγητή χημείας του Berkeley, κ. Παύλο Αλιβιζάτο, ο οποίος θα τιμηθεί αύριο με την απονομή του βραβείου Νίκη του AIT για τη διακεκριμένη συμβολή του στην ανάπτυξη της νανοτεχνολογίας. Ο κ. Αλιβιζάτος αποτελεί ένα λαμπρό πρεσβευτή των Ελλήνων επιστημόνων που διαπρέπουν στο εξωτερικό και ένα αξιοζήλευτο πρότυπο των νέων ανθρώπων του τόπου μας που σπουδάζουν, εργάζονται σκληρά και προσπαθούν να δημιουργήσουν στις αντίξωες συνθήκες της δυσάρεστης πραγματικότητας που βιώνει η Ελλάδα. Ο μεγαλύτερος ίσως κίνδυνος για τη χώρα μας από την έναρξη της οικονομικής κρίσης και για τα επόμενα χρόνια είναι η μαζική φυγή υψηλά καταρτισμένου ανθρώπινου κεφαλαίου προς το εξωτερικό, το λεγόμενο brain drain. Η σημαντική παρουσία απόψε μαζί μας τόσο νέων αξιόλογων ανθρώπων, καθώς και μια σειρά μικρές αλλά σημαντικές πρωτοβουλίες που αναπτύσσονται στον χώρο της νεανικής επιχειρηματικότητας, με την ίδρυση καινοτόμων startups, τόσο στον χώρο της πληροφορικής και των υπηρεσιών, όσο και αλλού, αλλά ταυτόχρονα και τα βήματα που πραγματοποιούνται στην Ελλάδα, ακόμα και στον ευρύτερο χώρο της νανοτεχνολογίας, αποδεικνύουν ότι υπάρχει ακόμα ελπίδα από μια γενιά που αποφασίζει να δημιουργήσει, να εξάγει, να καινοτομήσει. Ένα νέο οικοσύστημα φαίνεται να γεννιέται σε πείσμα των δυσκολιών που εξακολουθεί να δημιουργεί το κράτος και μακριά από αγκυλώσεις προηγούμενων γενεών επιχειρηματιών. Μαζί με όλα αυτά, οι αλλαγές στην παιδεία φαίνεται ότι δρομολογούν μια χαραμάδα αισιοδοξίας για το αύριο. Το AIT, που έκλεισε το καλοκαίρι 10 χρόνια λειτουργίας, αποτελεί παράδειγμα ενός τέτοιου μικρού οικοσυστήματος καινοτομίας και δημιουργικότητας. Νέοι επιστήμονες με διακρίσεις, όρεξη και όνειρα διδάσκουν, ερευνούν και διακρίνονται παγκοσμίως. Δεν είναι τυχαίο ότι η Microsoft κατέταξε το AIT στο 13% των καλύτερων ερευνητικών κέντρων παγκοσμίως, αναφορικά με το παραγόμενο ερευνητικό έργο στην περιοχή του ICT, ενώ στην Ελλάδα κατέχει την 7η θέση σε απορροφητικότητα ευρωπαϊκών ερευνητικών προγραμμάτων. Οι 465 απόφοιτοι του AIT από 25 χώρες βρίσκονται σήμερα σε ολόκληρο τον κόσμο. Από τις ΗΠΑ και εταιρείες όπως η Google, η Microsoft, η Motorola, την Ασία, τη Μέση Ανατολή, την Ευρώπη και τη χώρα μας και σε εταιρείες όπως η Huawei, η Oracle, η Ericsson, μέχρι φημισμένα πανεπιστήμια όπως το Imperial, το Carnegie Mellon, το California Tech και το Aalborg, οι απόφοιτοι του AIT αποδεικνύουν καθημερινά ότι η Ελλάδα μπορεί να αξιοποιήσει το ανθρώπινο δυναμικό της και να αποτελέσει και στην εκπαίδευση μια περιφερειακή δύναμη αναφοράς στον χώρο της Νοτιοανατολικής Ευρώπης και Ανατολικής Μεσογείου. Όλο αυτό το έργο παράγεται μακριά από τα φώτα της δημοσιότητας, έξω από τον κρατικό παρεμβατισμό και στο θολό νομικό καθεστώς της ιδιωτικής μη κερδοσκοπικής τριτοβάθμιας εκπαίδευσης. Κλείνοντας αυτή τη σύντομη εισαγωγή, θα ήθελα να ευχαριστήσω θερμά τον κύριο Αλιβιζάτο για την παρουσία του εδώ μαζί μας, να τον συγχαρώ εκ μέρους όλων των alumni clubs που συνδιοργανώνουν απόψε αυτή την εκδήλωση και να του ευχηθώ κάθε επιτυχία στη συνέχιση αυτού του μοναδικού επιστημονικού εγχειρήματος που θα αλλάξει τον κόσμο μας προς το καλύτερο. Θα ήθελα να καλέσω στο βήμα τον πρόεδρο του AIT, κύριο Πέτρο Βόκαλη, για ένα σύντομο χαιρετισμό. Σας ευχαριστώ θερμά.
I think we should start with switch to English. So welcome, ladies, gentlemen, dear friends. I would like, first of all, to thank the AIT Alumni Club, along with alumni clubs of Bentley, Berkeley, and Columbia University, for organizing with us this event. I think that in the current juncture of our country's development, gatherings such as this that bring together young people who share a common and quite high educational experience are critical in going ahead. And going ahead is what we need to do. accepting the Nikkei Award tomorrow. This is a very important event for the AIT in its short history. Following Dr. Econom, Dr. Mitropoulos and Dr. Panasselis, it is our great honor to honor you, sir. I will not speak about the, sorry, probably not, yes, sorry. So, what I wanted to say is not about the biography of Professor Alivisatos, who comes from a family of distinguished professors and scientists who have contributed greatly to this country in the past century. But I would like to share with you my experience from his visit today at AIT, where I was honored to meet a gentleman, a wise and kind man, who engaged with each and every one of our researchers and our scientists, was eager to listen, was eager to offer advice, and most of all share a word of encouragement, which is greatly appreciated in those days, and share with us his true and living agony about the future of the society. So it is a great pleasure to have you here, and please give us.
Σας ευχαριστώ πάρα πολύ για την αναγνώριση που μου έχετε κάνει με το βραβείο Νίκη, και πρέπει να πω ότι σήμερα είχα την ευκαιρία να κάνω μια επίσκεψη στο AIT και ήταν πάρα πολύ θετική εμπειρία για μένα. Βρήκα εκεί ομάδες ερευνητών, διεθνείς ερευνητών, δουλεύοντας σε πολύ υψηλό επίπεδο και κάνοντας πάρα πολύ ωραία δουλειά στην έρευνά τους. Και εκεί στην Αμερική που είμαι, δεν διαβάζουμε στην εφημερίδα την ιστορία του AIT. Ακούμε πολλά άλλα, αλλά δεν ακούμε για αυτά που νομίζω ότι είναι οι αποδείξεις ότι υπάρχει ένα πολύ καλό μέλλον εδώ. Λοιπόν, ευχαριστώ που μου δείξατε το AIT σήμερα και σας εύχομαι πάρα πολύ να πάνε πολύ καλά τα πράγματα όπως έχουν αρχίσει τώρα. Δυστυχώς θα πρέπει τώρα να αλλάξω από τα ελληνικά να πάω στα αγγλικά, διότι η αλήθεια είναι ότι δεν έχω το λεξιλόγιο να κάνω μια τέτοια ομιλία στα ελληνικά πλέον. Δεν έχω την ευκαιρία επίσης να κάνω εξάσκηση των ελληνικών μου τόσο συχνά. So I'm now going to switch. And I will tell you this evening a little bit about nanoscience and nanotechnology. Also, my goal will be to combine this discussion about this area of science with an effort to try to understand how it could contribute to the largest problems facing humanity in the coming decades, which surely is in areas of energy and environment. So I think the goal of every scientist should be to try both to make a big contribution in terms of ideas of just the pure science itself, but also to be thinking all the time about how to try to leave the world a better place as a result of the science that we are doing. So that's our goal here, is to try to understand this new field of science and also to see how it would connect potentially with energy and environment issues. And when we think about issues of energy and environment, certainly there are many, many issues, but certainly one that stands out is the fundamental fact that today's human energy use is based dominantly on fossil fuels, and the combustion process as we practice it today for all the usable energy that we get tends to leave carbon dioxide in the atmosphere. This year, almost 33 gigatons of CO2 will be put into the atmosphere globally, and of those 33 gigatons, approximately half will remain in the atmosphere for the long term, while half will be taken up by the oceans and by the land. So as we look forward to the future, we have even a more pressing problem, which is there are 2 billion people in the world today who live on $2 or less each day. And those people, every day they wake up thinking how they can get access to energy and how they can improve their lives, and we all need to help them do that. And as that happens, their energy use is going to increase enormously. So as we think about the future of energy, we know that we're going to need a lot more of it just because of the people that are trying to improve their lives. And yet at the same time, we know we have to reduce emissions. So this is very hard, and nobody quite knows how to do it. And we will need to have significant changes in the ways in which we produce and manipulate energy in order to meet those challenges. So we will look today at 3 aspects of energy. There are many, of course, and I'm only going to pick a few which are ones that I happen to have some interest in, and those will be solar photovoltaics, energy storage, and artificial photosynthesis. So that's a lot of topics right there. And we will look at how nanoscience can connect with those. It's important for me to remind you, I know most of the people here have a strong science background, but I do want to just remind you, because sometimes even the scientists tend to forget that actually the energy technologies that we do have all came from fundamental science. They did not exist before. Without the science of thermodynamics, or electricity and magnetism, of course, we would have no energy technology at all. And the photovoltaics, which I will discuss today, actually have an incredible history in fundamental science. You will perhaps recall that Einstein won the Nobel Prize. He could have won it for any 10 different things, but in practice, he won it for the photoelectric effect. And if you recall, in the photoelectric effect, it was the proof that quantum systems existed. He showed that a photon of sufficient energy could eject an electron from a solid. And below that energy, it could not. But it proved that the photon knocking out a single electron was a quantum object. And in fact, the use of solar energy today in photovoltaics is completely based on the photoelectric effect. So whenever you see a beautiful solar cell outside, you can know that that was the result of the discovery of quantum mechanics. Now, solar technologies are evolving, and they are evolving as science becomes deeper. The simplest thing that you can do if you want to use solar energy is put something out in the sun and let it get hot. So that's a solar thermal technology, and it's a certain level of science. Next higher level is the quantum use of the quantum nature of matter, and that's a solar photovoltaic. And then what I will say today is that the next higher level would be actually to use the sun to do photosynthesis, to make and break molecules in such a way that we actually create states of lower entropy using the energy of the photons. So there's an evolution of solar technologies. And right now, we're pretty good at solar photovoltaics, but not quite perfect. And we don't know how to do artificial photosynthesis at all. Now, before I go into the scientific description, there is one more thing I just want to remind us all of, which is, since in this case we want to do science in the service of society to solve a set of problems, in this case how to use solar energy better, it is important for the scientists to also stop and take a look and find out what is industry doing today, and to know specifically what the status of the world is in that respect. So solar photovoltaics now exist widely around the world. The first one was made in 1950 at Bell Laboratories. And the first photovoltaic that was made cost a few $100,000. So it was for a 1 watt system, a few $100,000. And today we've had a long learning curve where people have learned systematically how to make them better and better and better. And I just looked up the data. There's a website that in Taiwan that posts every day the current price of solar photovoltaic module. So I happened to look this up on October 31st, and the price of a solar module on that day was 67 cents a watt. So well below $1 a watt. $1 a watt for the module itself is a pretty good price. Of course, you have to then install it, and there are costs associated with the installation. But if you can bring the cost down to this level, even just a little bit more, you achieve grid parity. In other words, it's just as cheap to get your energy from a photovoltaic as it is to dig something out of the ground and burn it, which is an amazing thing to think about, that you can create an electronic manufactured product as cheaply as it is to just dig something out of the ground and light a match to it. It's a real triumph of manufacturing. As a result of the fact that the prices are dropping and dropping, we see that the deployment of solar energy is growing and growing. So, for example, at the end of 2011, there was just about 23 gigawatts installed peak for that year. In middle of the summer this year, there was already 27 gigawatts installed. So you can see that the growth is really happening very, very dramatically. And for all the reasons that I can think of, at least, given how low the fractional penetration of solar has today, there's every reason to believe that this growth will continue for at least a few more years, at which point we will enter the terawatt era for solar energy. And the United States is approximately, needs a power of approximately 13 terawatts. So as you start to enter into the terawatt era, you're now producing energy on a global scale that's a significant fraction of the total energy use that's going on in the world. So it's going to happen. It is important also to note, though, the megatrends that are going on in society at large. For example, here you can see these represent different countries, the different regions at least. This is the United States, here is Europe, and this is their fractional contribution to the solar market. And of course, you know, the solar cell was, for example, invented in the United States based on science that was done in Europe. But what you can see here is that at least the United States and, for example, Japan have become very, very small fractions of the total global production because right around here in the early 2000 period, China decided to get involved in this field. And in about a decade, they've gone from essentially non-existent to almost 3/4 of the market. So you can see here the global trends of the world manifesting themselves very, very clearly. Now, one more graph to show you here, and then we'll go to the real science of nanoscience a little bit. This shows the electricity production in a country that had a determined policy to alter their energy consumption, and that is Germany. And what you can see here in this, the yellow curve there represents the fraction of their energy that was obtained from solar energy on this particular day, May 25th, 2012. And on that day, there was, at peak, there was 22.5 gigawatts of solar energy. 40% of all electricity produced on that day was from solar. And if you integrate over that day, because of course the sun only shines brightest in the middle of the day, if you integrate over 24 hours, it was 14% of electricity. And now, of course, what this points out is that if you are in a country where you start to get to the point where you get this amount of solar penetration, you really, really start to think about how you're going to store the solar energy. And that's a very fundamental issue that remains, is there's not a solution really that's satisfactory to how to do that. If you're like me, you see this graph and you wonder a little bit, okay, May 25th might have been the best, you know, the only day of sunlight in all of Germany, you know, for the year. But in fact, not so. If you look, what you can see here is that actually from May through August, the production was pretty constant at about that level that you just saw. But of course, in the winter months, it does tail off. And so again, that's another reason to want to have a good system for energy storage. And you'd like in the summer months when there's more sun to create some form of energy that you can use later on in the winter. Okay, so conclusion. Solar industry is growing, but anything we can do to improve dollars per watt is a good thing. And there may be things that we can do to help that. And bottom line, better find a practical way to store the energy. Okay, so now we're going to switch gears and have a brief, 5-minute university version of what is nanoscience. And what I'd like you to really, there are many themes to nanoscience, and here I'm listing some of them. They concern scaling laws, building blocks, what I call the power of one. When you study nano objects, you have to go in and look at them one at a time. The very, very deep connection between nanoscience and biology, and a little bit about how we're building today. I won't go through all of those, but if there's one thing I hope you'll remember from this, it will be the scaling laws. And since we're here in Greece, I thought that we would discuss the scaling laws in terms of one of the all-time greats, Democritus, who conceived of one of the most interesting thought experiments anyone has ever thought of. So let's just go over that, and actually that's all you need is Democritus's idea, and you can become a card-carrying nanoscientist. So let's think about that. His idea was, let's take a material like gold, and if you take gold and you enter it into Google and you say, what is the melting temperature? It will say the melting temperature is a certain temperature. And if you ask, what is the specific gravity, what is the hardness, and so on, there'll be a list of all of the properties. And Democritus said, let's take this thing and split it into two pieces and ask, what do I have when I've broken it into two pieces? Is it still the same thing or not? And of course, we all know from our experience that if we take a macroscopic object and cut it in two, the two pieces are fundamentally the same. Their intrinsic properties are not changed. But he had a very active discussion going with his friends, and they just said, well, let's do that again, and again, and again, and do successive division, and he intuited this idea that at some point matter would not be continuous, it would become grainy. And the point at which it becomes so granular that you're down to a single grain, he called the atom, or the indivisible, that which cannot be broken up. Now, of course, we know today that there are subatomic particles, but the idea, of course, was correct, that the fundamentals of matter are built up from things which are the elementary units of atoms. What's interesting for the nanoscience point of view is that when you go from continuous matter to the atom, there has to be something in between. There's a point where, let's say you only got 1,000 atoms across, and you chop it in two and you go to 500. And you chop it in two and you go to, say, 250, and then 125, okay, at some point, there's a lot of things that are now not going to be true for that 125 atom little crystal that would be true for a big macroscopic one. So the intrinsic properties will no longer be the same. And of course, the subject of nanoscience concerns itself with understanding how the properties depend upon the size when things are very, very small, according to what we would call the scaling laws. So I'm going to show you a few scaling laws, just real quick, and you'll see how those then can be used to design new materials. So the first one that we're going to study is melting, because I just gave you that example. I said if you look up the properties of a solid, one of the things that you will almost always see listed is the melting temperature. So let's take very small crystals. That's what's shown here. This is from work we did a few decades ago. And if you look at the melting temperature of a semiconductor, the kind of material you would make a solar cell out of, as you make it 5, 4, 3, 2, 1 nanometer, so this is where we're going from, say, a few thousand atoms down to maybe about 100, as we change the size of the crystal, the melting temperature changes by hundreds of degrees. This isn't a little effect, it's an enormous effect. And you can understand why. The crystal is held together by every atom grabbing every other. But when there are so few of them, they actually don't hold each other in quite as tightly, and the crystal melts at a lower temperature. So already we have an observation here that's of quite a bit of interest for us from a very practical point of view. Because if we want to make a solar cell, what we want to do is make it fast. And when we want to make it fast, what that means is we want to make a good crystal in a short period of time. Well, if we can start with small crystals and they melt at a low temperature, then perhaps we can cast a film onto a fast-moving substrate, and in that way we can grow a high-quality film in a short period of time. So that's a goal that one has for the solar cell industry, and there's a whole bunch of companies out there that are working away at trying to take these small particles and anneal them very quickly in such a way that they would make a high-quality film. One of the things that we work at in my research group is to try to image. So here you can see an image of small crystals that are being heated in a liquid, and you can see the little crystals moving around, and every so often you'll see that they two of them will kind of collide, like right there in the right-hand corner, the two of them just collided, and they started to join together. And we found ways to image this at the atomic level so that we can observe the details of how these crystals join. And so, for example, in this case, when the crystals are joining, and we can now take frames from that movie, we can see how they join, how atoms move around, and how they fuse together. And as we understand that better and better, we can then try to go in and apply that to the growth of a thin film solar cell in a more systematic way. So you saw one scaling law. So now another one. I'm going to give you one which is a very easy one. I see here that this is one you will have, and looking at the age group and everything here, my guess is everyone will have experienced what I'm about to talk about. Let's say that you are madly in love and you want to go and buy a beautiful diamond ring, okay? That's a nice position to be in, except you encounter this issue, which is you enter into the store and you figure you would like to buy the largest diamond possible. And pretty soon you discover a scaling law. You may not have understood that you're encountering a scaling law, but there is one. The scaling law is every time the size of the diamond doubles, the price goes up by 4. This is why you end up with a certain size that you're going to get. You're not going to get a bigger one because, you know, it just can't be done. Doubling 4 times the price, you know, you hit your budget. Why is this? And this is now going to be very fundamental for nanoscience, okay? This has to do with what it takes to remove a defect from a solid. So imagine that a diamond is forming somewhere in the earth, and as the atoms come together to make the crystal, occasionally there is going to be a mistake. There will be an atom in the wrong place. That's a defect. And if you have a lot of defects, the diamond will become of low quality, and nobody wants to buy it. It's not a good one. What you have to do with a normal crystal is wait, heat it up, and wait for the defects to anneal. But it turns out the time for a defect to leave a crystal is related to its size. Actually, it scales exponentially with the volume. This is why a big crystal is of high quality is so rare, because it really takes a long time for any mistakes in the growth to be healed, and that's why you have to pay a lot for a diamond. Well, okay, so that tells you about the diamond industry, but what about nanoscience? Well, now we're in a very interesting position because we can turn it upside down. What I want now is to make a tiny crystal, not a big one. And the lesson is little crystals, they should be very easy to make. And in fact, there is a proof that that is true. It turns out that when you make very tiny crystals, almost invariably, without a lot of effort, there are ways to mess them up, but with just a little bit of care, you can take tiny crystals and push all the defects out to the edge, and the crystals will be essentially perfect on average, which is something which for big crystals is almost actually even possibly actually impossible to do, but certainly in practice extremely hard. With little crystals, it's not. What that means is if we make very tiny crystals and we learn how to use them well, we can make perfect materials with very little time and energy. As we try to make large-scale energy technologies, that's going to turn out to be very important. I show here just a very quick example of one of the ways we know what I just said, which is we can take small crystals and we can apply to them a lot of pressure, just like you might in a diamond. And it turns out when you take a tiny crystal and you squish it, it will occasionally undergo a phase transition to a more dense phase. The atoms will rearrange themselves. But that will almost always nucleate at a defect. The change in the crystal will nucleate at a defect site. It turns out if you take a sample of tiny crystals, you can't get them to undergo these phase transitions. They're so perfect, they just resist finding a way to nucleate. And another thing that we found in this work was that we could take a small crystal, super pressurize it, 3-4 times the normal transition pressure. Finally, it would undergo a transformation. It could change its volume by 20%. And it would just do that, pop over to a new structure. You release the pressure, and eventually it pops back. And you could just go back and forth, back and forth. If you tried to do that in a big crystal, the crystal will crack into 1,000,000 pieces. That turns out to be really important for batteries. Imagine that you have a battery and you've got lithium going into a lithium ion impregnating into an electrode. That's how you store lithium ions. There's a big volume change. Every time you do that, when the volume changes, if you have a normal battery, you all know that eventually you'll cycle this thing, say 500 times, and eventually it won't store energy anymore. Really, the battery falls off in its behavior. That's because the materials inside, when those volumes are changing, crack up into little tiny pieces and they just become less and less usable. But it turns out if you start with a nanoscale material, you can do this volume change over and over again in a very reversible way. So again, the nanoscience could help us make a better battery. Okay, we've got 2 more scaling laws. Hang on with me, I'm going to do them quickly. I reminded you at the beginning about quantum mechanics and how quantum mechanics was discovered really essentially with solar energy. Well, now let's look at a so-called quantum dot, and I'd just like to explain to you what we mean by that. When we have a photon incident on a solid and it's above a certain energy, it will knock an electron loose from one of the chemical bonds. And that electron will start to run around inside the solid. But when we talk about an electron running around, we know that that means it's a wave. And it has a characteristic wavelength. And if the crystal is small compared to the wavelength of the electron, then the energy of the electron is changed. The smaller the crystal, the faster the electron moves. It feels the boundary of the crystal and it moves very fast. It's a little bit like those balls. If you've ever been at one of those science museums, they'll have this big circular track for a ball, and the ball falls in towards the center and goes faster and faster. It's a little bit like that. As you confine an electron to a smaller and smaller volume, the kinetic energy of the electron goes up and up and up. That means that the photon, to excite the electron, actually has to be higher in energy in order to create that excess kinetic energy. And that changes systematically the energy of the semiconductor as a function of the size. And it makes, for example, this beautiful set of colors that you see on the right there for so-called quantum dots. So I've spent about 30 years now studying quantum dots. And they're wonderful little objects, and they show these beautiful quantum behaviors. And in fact, something that I worked on very hard in earlier days in my career, but not the topic of the discussion today, is how quantum dots could be used to image in biology in ways that organic dyes, for example, are not very suitable for. And so that's a whole story that we're not going to do. What we're going to do quickly is just how could we think about making a solar cell where instead of having a big crystal, we're going to have a tiny one. There are many problems, for why people might at first say, don't go there, this is a bad idea. But we're going to try anyway and see what happens. So what we're going to try to do is just make an array of very tiny crystals and see if we can get charges to move through them. Now, why would that happen? Normally you would just think to yourself, well, if there's an electron bouncing around in one crystal, it'll stay there. Why should it go to the one next to it? But remember what I told you is the crystal is now small compared to the wavelength of the electron. So the electron, as a wave-like particle is going to try to escape from the crystal that it's in. The wave function of the electron will leak out past the boundary of the crystal. And if there's another crystal nearby, actually the electron can hop. The electron could potentially hop from one to the next. Now we're almost there towards making a solar cell. There's just one small detail that we have to consider. So this would be a solar cell now, where instead of having a continuous semiconductor, we would have little crystals. And instead of heating the little crystals up to make a film, we'll just cast them at room temperature as a little film, and we'll play with the quantum mechanics to get charges to move across that thing. That's our goal. Now, this is one technical slide. If you don't like the technical slide, just turn off for a moment. This will be quick. There's one thing we have to fight against. The smaller the crystal, the more you would think that an electron would tunnel from one crystal to the next. But there's one scaling law, this is the last one we're going to do, that I have to tell you about, and that is the scaling law called the charging energy. Imagine going back to a piece of gold. Imagine that I have a piece of gold, and I add one extra charge to it. I have changed the number of charges on that crystal by 1, and I have increased the charge density by 1 crystal divided by the volume of that crystal. So if I have a crystal that's 100 nanometers in size and I add 1 electron, it's no big deal. But if it's a 10 nanometer crystal and I want to add an extra charge, I have to increase the charge density by now quite a bit, because that electron is in a very small volume, and so are all the other electrons. So the charging energy becomes bigger and bigger the smaller the crystal becomes. It scales like 1 over the radius, actually, in a classical model. So this is a problem I have. If I want charges to move from one crystal to the next from quantum mechanics, I need to make them as small as I possibly can, because that will promote tunneling from one particle to the next. But if they become very, very small, the charging energy will prevent the charge from moving from one to the next. So there's probably some optimum size. So we sit there trying to make crystals of different sizes, and guess what? We find that there's an optimum size. And so now we feel like, oh, maybe we could go and make a decent solar cell out of this. Who knows? Okay.